In the mountains of northern Chile, a new telescope is preparing to change the way humanity watches the sky. Most telescopes are built to look deeper into space, or to capture sharper images of a single object. The Vera Rubin Observatory is different. Its purpose is to return to the same regions of the sky again and again, compare what it sees with what was there before, and detect anything that has changed. That idea may sound simple, but it could transform astronomy. The night sky looks calm when we see it from Earth. Stars appear fixed, constellations seem permanent, and space feels almost frozen in time. In reality, the universe is constantly active. Asteroids move through the solar system, stars change brightness, black holes flare when matter falls into them, and distant stars can explode in galaxies far beyond our own. Many of these events are temporary. If astronomers are not looking at the right place at the right time, the most important part of the event may be missed. For centuries, astronomy worked mostly through separate observations. A telescope would point at a part of the sky, take an image, and scientists would study what was captured. Later, someone might return to that region and compare it with a newer image. But the gap between those observations could be days, months, or even years. During that time, a supernova could appear and fade, an asteroid could pass near Earth, or a strange object could briefly brighten and disappear before anyone noticed it. Rubin Observatory was designed to solve that problem by turning the sky into a long-term survey of change. Its main project, the Legacy Survey of Space and Time, will repeatedly image huge areas of the southern sky over a period of 10 years. Instead of producing only a static map of space, the survey will create a time-based record of how the sky changes. This means astronomers will not only know where objects are, but also how they move, brighten, fade, appear, or vanish. At the center of the observatory is one of the most powerful digital cameras ever built for astronomy. It has 3.2 billion pixels, which allows it to capture extremely detailed images of large regions of the sky. Each exposure can contain stars, galaxies, asteroids, and faint distant objects all at once. But the real strength of Rubin is not only the size of its camera. The most important part is what happens after each image is taken. When a new image arrives, software compares it with older images of the same region. Most objects will match what was seen before, but some will not. A small point of light may have shifted position. A star may have changed brightness. A distant galaxy may show a sudden flash. An object may appear where nothing was visible earlier. These differences are treated as possible discoveries, and they can be turned into alerts for astronomers around the world. This makes Rubin Observatory almost like an early warning system for the changing universe. Instead of waiting for scientists to manually search through images, the observatory can identify possible changes quickly and send that information to other telescopes. If an event is temporary, speed matters. A supernova changes rapidly after it begins. A strange flash may fade within hours. An asteroid's orbit becomes clearer only after multiple observations. Rubin is built to notice these events early enough for follow-up observations to happen, while they are still scientifically valuable. One of the most important areas where Rubin could make a difference is asteroid detection. Most asteroids are harmless remnants from the early solar system, but some pass near Earth. A distant asteroid does not look dramatic when it is first detected. It may appear as a faint point of light moving slowly against the background stars. By itself, one observation is not enough to understand the object. But if the same point is seen again on later nights, scientists can measure its motion, calculate its orbit, and predict where it will go. That is why repeated sky surveys are important for planetary defense. The earlier a near-Earth object is found, the more time scientists have to track it and understand whether it poses any risk. Rubin Observatory is not a spacecraft sent to intercept asteroids, but it can help build a much larger map of moving objects in the solar system. Some of those objects will be ordinary asteroids. Others may be comets, distant icy bodies, or near-Earth objects that deserve closer attention. Rubin will also help astronomers study events far outside the solar system, especially supernovae. A supernova happens when a star reaches the end of its life and explodes with enormous energy. From Earth, it may appear as a new point of light in a galaxy that previously looked normal. These explosions are important because they reveal how stars die, how elements are spread through space, and how distances across the universe can be measured. The early phase of a supernova is especially valuable. The first light can carry information about the star before it exploded, and the physics of the explosion itself. If astronomers discover the event too late, some of that information is already gone. Rubin's ability to compare the sky repeatedly could allow scientists to catch more supernovae near the beginning, giving other telescopes time to study them before they fade. Supernovae also connect to one of the biggest mysteries in modern science: dark energy. Scientists know that the universe is expanding, and observations show that this expansion is speeding up. The unknown cause of that acceleration is called dark energy. The name does not mean scientists fully understand it. It simply describes a mysterious effect that can be measured but has not yet been explained. By observing huge numbers of galaxies and exploding stars over time, Rubin may help scientists improve their measurements of how the universe has expanded and whether our current models are complete. Another major mystery Rubin will help investigate is dark matter. Dark matter cannot be seen directly because it does not emit or reflect light, but its gravity affects the universe around it. Galaxies rotate in ways that suggest far more mass exists than we can see. Light from distant galaxies can be bent by invisible mass between the galaxy and Earth. Large-scale structures in the universe also show patterns that point to the presence of unseen matter. The observatory is named after Vera Rubin, the astronomer whose work helped provide strong evidence for dark matter through the study of galaxy rotation. In a fitting way, the telescope that carries her name will continue exploring the invisible universe, not by photographing dark matter directly, but by measuring the effects it leaves on visible objects. Distorted galaxy shapes, gravitational lensing, and large cosmic patterns can all help scientists understand how dark matter is distributed. The most exciting part of Rubin Observatory may be the discoveries that cannot be predicted. History shows that new ways of observing the universe often reveal things scientists did not expect. Radio astronomy led to the discovery of pulsars. X-ray astronomy revealed violent environments around black holes. Infrared astronomy exposed stars forming inside clouds of dust. Rubin adds a new kind of observing power by focusing on time. It is not only asking what exists in the universe, it is asking what is happening. A future alert from Rubin might first look ordinary. It could be a flash of light in a distant galaxy or a faint object moving through the sky. But after more observations, the event might not fit known categories. It may fade too quickly for a normal supernova, move differently from a typical asteroid, or change color in a way scientists do not expect. Other telescopes would then turn toward it, researchers would compare data, and a new mystery could begin. That possibility is what makes this observatory so important. Rubin is not only a tool for confirming what astronomers already know, it is a tool for finding the unexpected. A single strange alert could lead to a new asteroid, a rare stellar explosion, a better understanding of dark matter, a clue about dark energy, or an entirely new type of cosmic event. Unlike many space missions, Rubin does not travel anywhere. It does not land on Mars, fly past Jupiter, or orbit a distant planet. It remains on Earth, watching the sky from one of the best observing locations in the world. But its reach is enormous because it can monitor billions of objects over time. From one mountain in Chile, it can help track nearby asteroids, study distant galaxies, catch dying stars, and build one of the most detailed records ever made of the changing universe. The power of Rubin Observatory is not only in its technology, it is in its patience. Many cosmic events are easy to miss because they are faint, fast, rare, or unexpected. Rubin is designed to keep looking, keep comparing, and keep asking whether the sky has changed. Over 10 years, small differences will add up into a massive record of motion, brightness, darkness, explosions, disappearances, and surprises. The night sky may still look peaceful when we look up from Earth, but that peaceful appearance hides constant activity. Objects are moving, stars are dying, galaxies are changing, and light from ancient events is reaching us for the first time. For most of history, many of those changes passed unnoticed. Now, with Rubin Observatory, humanity has built a machine designed to notice them. Some discoveries will be small, others may reshape astronomy. A few may be things no one predicted at all. That is the real promise of the telescope that will catch the universe changing. It is not only searching for answers, it is watching carefully enough to find surprises. I'm Astro Artemis, stay curious crew.